Welcome students. Our today's topic is related to fluorescence spectroscopy and polarimetry. Let's start with the origin of spectroscopy. Light is supposed to have dual characteristics, that is corpuscular and waveform. Thus a beam of light may be understood as an electromagnetic waveform disturbance or photon of energy propagated at 3 × 10⁸ meters per second, that is at the speed of light. The electromagnetic radiation is made of an electrical and magnetic wave which are in phase and perpendicular to each other and to the direction of propagation of wave. The figure shown is the representation of a ray of plane polarized light. The magnetic vector, which is unshaded, and the electric vector, which is shaded, are perpendicular to each other and to the direction of propagation of wave. The wavelength lambda is the distance between the two consecutive crusts or troughs. Electromagnetic radiation is produced by events at the molecular, atomic or nuclear level, for example, oscillations of nuclei and electrons in electrical or magnetic fields, molecular bending and vibration, excitation of orbital electrons and ejection of an inner orbital electron, etc. These events differ in terms of energy involved, and hence the radiation they emit will have different wavelengths. Thus a complete spectrum of electromagnetic radiation will be produced. A branch dealing with the study of different spectra produced by electromagnetic radiation is referred to as spectroscopy. Spectroscopy is broadly classified into three main types depending upon the type of radiative energy, the nature of interaction, and the type of material. Regarding the type of radiative energy involved, spectroscopy can be classified into many types, like those involving electromagnetic radiation, which was the first source of energy needed for spectroscopic studies. Such techniques are typically classified on basis of wavelength region of the spectrum and include microwave, infrared, near infrared, visible and ultraviolet, X-ray and gamma spectroscopy. Those involving the particles with de Broglie wavelength, which can also be a source of radiative energy, commonly involving both electrons and neutrons. The third is the acoustic spectroscopy, which involves radiative pressure waves. And the fourth one includes the mechanical methods that can be employed to impart radiating energy similar to acoustic waves to solid materials. The second classification is based on the nature of interaction, which may include the absorption, which occurs when energy from the radiative source is absorbed by the material, the emission, which occurs as a result of release of radiative energy by the material, the elastic scattering, and reflection spectroscopy, which is based upon how the incident radiation is reflected or scattered by the material. It also includes the impedance spectroscopy that studies the ability of a medium to impede or slow the transmittance of energy. Furthermore, it also includes the inelastic scattering phenomena, which involves an exchange of energy between the radiation and the matter that shifts the wavelength of the scattered radiation, for example, Drummond and Compton scattering. Last but not least is the coherent or resonance spectroscopy, where the radiative energy couples two quantum states of the material in a coherent interaction that is sustained by the radiating field. The coherence can be disrupted by other interactions such as particle collisions and energy transfer, and so often require high intensity radiation to be sustained. One of its examples is nuclear magnetic resonance spectroscopy. The technique is also classified on basis of the type of material, which can be an atom, a molecule, a crystal, or nuclei, giving birth to techniques like atomic absorption spectroscopy, atomic emission spectroscopy, UV visible spectroscopy, infrared spectroscopy, Raman spectroscopy, fluorescence spectroscopy, as well as X-ray crystallography, X-ray fluorescence, and NMR spectroscopy. Our topic is related to the study of fluorescence spectroscopy. Fluorescence spectroscopy is the phenomenon whereby a molecule, after absorbing radiations, emits radiation of a longer wavelength. The phenomena of luminescence was first studied by Stuck in about 1852. Luminescence is a general term to describe systems that can be made to glow. Such systems can be classified according to the glow producing mechanism. The two major divisions of the present day analytical importance are fluorescence and phosphorescence. The compounds that exhibit fluorescence or phosphorescence contain either an electron donating group, which can be amines, alcohols, and heteroatoms, or multiple conjugated double bonds, that is, aromatic rings containing either non-bonding electrons or pi electrons. The presence of groups that tend to withdraw electrons like carboxyls, azo groups, and halides, etc., usually destroy the phosphorescence. Fluorescence spectroscopy is becoming more and more popular instrumental technique for providing direct and indirect exploratory information about chemical and physical properties of food products because of the high specificity and high sensitivity. Also, the several substances that are inherent to food systems such as proteins, vitamins, pigments, toxins, flavoring compounds exhibit intrinsic fluorescence. Fluorescence spectroscopy analysis often involves the use of an extrinsic probe developed for specific analysis. It may also require sample preparation step before the fluorescence measurement to reduce the effect of other influencing parameters. However, for food analysis, the intrinsic fluorescence of the intact food, called autofluorescence, can be measured. The use of autofluorescence increases the speed of analysis considerably, facilitates non-destructive analysis, and makes fluorescence a potential method for online or at-line applications. The basic principle of fluorescence is that when an atom or molecule absorbs light, the energy of photon absorbed lifts an electron to a higher orbital. The excited electron can now return to the ground state in either of the two ways. It might do so in one single step by emitting light radiations of same wavelength as that of the absorbed. The electron might, however, also return to the ground state in a stepwise manner through intermediate energy levels, emitting quanta of radiations corresponding to each energy level. Since each quantum will have a smaller amount of energy, the radiation emitted will have a longer wavelength than the original wavelength absorbed. Accordingly, the emitted light radiations will have many different wavelengths corresponding to each intermediate energy level that electron adopts on its journey from excited state to the ground state. Therefore, fluorescence spectra are band spectra that are usually independent of the wavelength of radiation absorbed. Thus, each molecule or substructure that's able to emit fluorescence, called a fluorophore, exhibits the fluorescence properties. For example, in only an ideal case, the excitation and emission spectra are identical and can be considered as mirror images of each other due to the same electronic transition taking place. The visual appearance of emission spectrum does not depend on the excitation wavelength. The use of both excitation and emission spectra gives fluorescence spectroscopy of a high degree of sensitivity, and two molecules with similar excitation spectra may have different emission properties. Phosphorescence is a similar but slower luminescence phenomenon in which the excited molecules go through an intermediate excited triplet state from where light is emitted by returning to the ground state. The instrumentation and spectral region for measurement of phosphorescence are almost identical to fluorescence spectroscopy. There are several factors that affect the process of fluorescence, which include quenching, inner filter effects, concentration, molecular environment, and the scatter. The fluorescence intensity may decrease as an effect of intra or intermolecular interactions, either with the fluorescent molecule itself in the solvent or with the other molecules in the sample matrix. This phenomenon is called fluorescence quenching. Another type of mechanism that will reduce the measured fluorescence intensity is the so-called inner filter effects, which are due to the absorption of emitted light by either the fluorophore itself or by chromophores in the sample matrix. Inner filter occurs when a chromophore reabsorbs the emitted fluorescence, or when a non-fluorescent chromophore absorbs parts of the excited light, resulting in decreased fluorescence intensity or distortion of band shapes. Furthermore, like absorption spectroscopy, fluorescence spectroscopy depends linearly upon the concentration. It has to be within a certain concentration range in order to avoid the artifacts such as quenching and inner filter effects. For transparent solutions with absorption below 0.05, the fluorescence intensity is linearly related to the concentration of the fluorophore. In addition to concentration, fluorescence intensity depends on the molecular environments such as polarity, pH, temperature, etc. Scattering of light is also a phenomenon that may disturb the measured fluorescence signal. Light is primarily scattered by small particles in the samples and is observed by the fluorescence detector as false emitted light. Let's talk about the instrumentation, that is spectrofluorometer. The main components of a spectrofluorometer are a continuous source of radiant energy like a mercury lamp or a xenon arc, a monochromator, usually a prism, to choose the wavelength with which the sample is to be irradiated, a second monochromator placed after the sample, which enables the determination of fluorescent spectrum of the sample, a detector, usually a photomultiplier suited for wavelengths greater than 500 nanometers, and an amplifier. The spectrofluorometer is used for the applications like fluorescent probes and studies on membrane structure, assay of membrane potential, fluorescent microscopy, intracellular free calcium concentration assay, in which the chelation gives rise to fluorescence whose magnitude is proportional to the free calcium ion concentration in the cytosol. Since fluorescent emission is extremely sensitive to local environment, it can also be used to monitor kinetic and thermodynamics of the incorporation of a particular subunit or substrate into macromolecular assembly. Apart from these applications, fluorescence has been applied on various kinds of food, from fish and meat to fruit and vegetables. The 4 specific examples of food fluorescence applications include direct fluorescence measurements, which has been used in relatively few studies of food product like riboflavin, which is a highly fluorescent molecule with excitation maxima at 270, 370 and 450 nanometers and emission maxima in the range of 525 to 531 nanometers. The content was determined chemically in plain yogurt exposed to light for up to 35 days and subsequently predicted from fluorescence measurements by chemometrics. The second is indirect fluorescence measurements, which has been used to predict some of the oxidative parameters like lipid oxidation, as the exposure of the products like cheese, meat and other lipid containing products to light and oxygen for a long period leads to off flavor development, discoloration, nutrient loss and formation of toxic compounds which rapidly impair the product quality. The third important application is pertaining to food authenticity, which is about analyzing the food purchased to match their description. For example, the content should be equal to what is claimed. The geographical, vegetable or animal origin should be as described, where the high sensitivity of fluorescence spectroscopy makes it possible to detect compounds in parts per billion levels. The fourth application is about the fluorescence and process analytical technology. Process analytical technology is a new concept introduced within the pharmaceutical industry, but the principal focus has been on the food industry for a number of years. It refers to measuring the relevant information at the relevant time during the production, which can be the incoming raw material, some process streams or process parameters, or the finished product. We will now discuss the process of polarimetry. Polarimetry is a sensitive, non-destructive technique for measuring optical activity exhibited by inorganic and organic compounds. A compound is considered to be optically active if linearly polarized light is rotated clockwise or counterclockwise when passed through it. The amount of optical rotation is determined by the molecular structure and concentration of chiral molecules in the substance. Polarimetry was discovered by Antoine Louis Mals, a French engineer who was studying reflection of glass. Several years later, another Frenchman, Jean-Baptiste Biot, found that molecules such as sugar could not rotate light as well. Its instrument called polarimeter is a device used for the measurement of optical rotation, and its scheme is depicted in the given figure. The main components of the polarimeter are a light source, which is usually a sodium vapor lamp, a polarizer like a Nicol prism, an analyzer which is also a Nicol prism, and a sample tube. The polarizer is used to obtain polarized light, while the analyzer is used to measure the angle of rotation. The sample tube should be filled with the sample in a way that after the filling, a convex surface of liquid is formed on the tube thread. This surface is then cut off with a lens. This procedure needs to be performed quickly in order to avoid the formation of gas bubbles in the sample tube. After screwing the tube thread, the filling of the tube is checked. The tube is wiped and inserted into the polarimeter. The technique has many applications. The industries that produce or use chiral organic molecules in pure or diluted form, rotation of mixtures like food ingredients, perfumes, flavorings, chemicals, pure or formulated pharmaceuticals are observed. In these situations, polarimetry provides a rapid and reliable quality check that eliminates the need of conventional analysis like liquid chromatography, which is a time-consuming technique employing almost an hour to do the similar analysis that a polarimeter can reveal in minutes. Polarimetry provides an additional check on a pure substance before it is added to an expensive batch to determine the ingredient's concentration or purity. For example, a 25% glucose syrup will have an observed rotation that's 5/6 that of a 30% syrup. The optical rotation of a mixed component ingredient, intermediate or finished product will have a characteristic optical rotation that may arise from the presence of several chiral compounds. Once a standard is determined for the composite observed rotation, one can establish quality criteria based on optical rotation. In these situations, the polarimeter measurement becomes a type of screen for further testing to determine which ingredient is out of the specification. Polarimeter is used by organic chemists to test the effectiveness of catalysis and asymmetric synthetic process. Many optically active chemicals such as tartaric acid are isomers. A polarimeter can be used to identify which isomer is present in the sample. If the polarized light is rotated to the left, it's a levorotatory isomer, and if rotated to right, it's a dextrorotatory isomer. It can also be used to measure the ratio of these enantiomers in the solution. Concentration and purity measurements are especially important to determine product or ingredient quality in the food and beverage and pharmaceutical industries. Samples that display specific rotation that can be calculated for purity with a polarimeter include steroids, diuretics, antibiotics, narcotics, vitamins, analgesics, amino acids, essential oils and polymers. Starches, which are the most abundant substances in nature and used in various sectors of the food and pharmaceutical industry as well as the building sector, polarimetric quality control of starches therefore is important in various industries. Polarimeters are used in the sugar industry for determining the quality of juice from sugarcane as well as the quality of refined sucrose. Often the sugar refineries use a modified polarimeter with a flow cell, and when used in conjunction with a refractometer, it's called a saccharometer. This is all about our topic today. I hope you have understood well. Thank you very much.